Okay. uh, Please fill out the Google form. I hope you can access the Google form that is uploaded in the chat box for your attendance. Okay. Do not type your roll number in the chat box. Only fill out the Google form. I hope you don't have any issue with the Google form. Please do that. Can you access the Google form that is provided to you?
No, sir.
Oh,
No, sir.
No, sir.
No, sir.
just 1 minute. Manage how responses are collected. Presentation. Is it limited to? What is that setting? Responses. Oh, I see. This is by default. I think now you should be able to access. Please try again. Accessible, right? Just type in your own number and name there. That's sufficient. Yeah, I see that you have filled up the form. So before your CAT 1, we had one lecture on Tensor, but I didn't want to go into detail because I knew that there would be a long gap between that lecture and the consecutive lecture. So it's a problem. If there is no continuity in the lecture, whatever was introduced, that might have been forgotten also by now. Therefore, we can consider this today's lecture as the first lecture in tensor analysis. So tensor, it is just a mathematical concept, right? So just like your, see, I think like as a physicist or as an engineer, we can say that mathematics is our language of expressing or defining or explaining things, because hardly without mathematics a physicist and an engineer cannot express like the natural laws in physical sciences. So yeah, so far in this language that we use till now in our elementary sciences and all, we can define our physical system using a quantity called vector and scalars. Okay, there are certain physical quantities that we define as scalars and certain other quantities that we define as vectors. Because if you remember in the gradient divergence and all, we discussed a vector field, scalar field, scalar potential, vector potential, in the case of electricity and magnetism also. So most of the physical quantities that we encounter in nature, we can define it using the mathematical concept called vector concept and the scalar concept. So using vector concept and scalar concept, we can express most of the fundamental physical laws, right? But when the knowledge in physics and also the tools available to us due to the technological development have uh, enabled us to realize that there are certain physical systems where we need to consider what is called anisotropy. So in such cases, when we need to consider anisotropy, like in the case of this conductivity tensor, for anisotropic crystals, this conductivity, which was, as we know it, it's a scalar quantity, conductivity as a scalar quantity, conductivity, resistivity, and all, they are reciprocal to each other. They are considered as they are classified as, or they are already understood as a scalar quantity. But when we consider anisotropic systems, when the property of a certain physical system like material can no longer be isotropic or can no longer be identical in every direction, if such system has now what is called a preferential direction. So under such concept, we can no longer represent this conductivity as a scalar quantity. We can no longer represent this conductivity as a scalar quantity, nor this conductivity can be represented as a vector quantity. So beyond the scope of such vector and scalar mathematics, vector and scalar algebra, beyond such scope, we have to implement a new mathematical tools called tensors. Okay, so tensor analysis or tensor representation is simply one of the mathematical tools, right? Under tensor, we are going to represent scalar quantity, vector quantity, as well as other physical quantities that cannot be defined within the scope of vector and scalar. So this is just a mathematical tool that we will use to represent the general physical system. It can represent anything in nature. Okay, so I think Albert Einstein was the first person to introduce this kind of mathematical tools for representing like some system, physical system that is beyond the scope of this Newtonian laws. Like when he introduced general theory of relativity and all, uh, his the concept of vector and scalar was not sufficient to describe or to explain or to represent as a language, say to represent your curvature of space and all such things. He cannot use the vector and scalar to write down the mathematical description of such curvature of space and all, right? So because of that, I think he was elaborately, and he was using this tensor representation efficiently to represent vectors, scalars, and all other physical quantities in general, which cannot be defined within the scope of vector and scalars. So uh, his idea or his understanding of this general theory of relativity was explained using the language called tensor analysis, tensor representation. Okay, so as I said before, for such anisotropic system, this conductivity is no longer a scalar. It has what is called, it's neither a direct, it does, I don't mean to say that it has a direction like a vector quantity, but it is no longer a scalar. We cannot simply represent it using a scalar. So it now is what is called a tensor. We can only represent it using a tensor. So how we were presenting this conductivity here, as you see it cannot be a scalar. In order a scalar quantity, if you just multiply with a vector quantity, it will just simply multiply the same. Like for example, if conductivity is purely a scalar, then when you multiply with this vector quantity, the first component, that is J1, is also multiplied with scalar sigma. The second component, J2, is multiplied with sigma. The third component of the vector is also multiplied with what is called sigma, the same quantity. But when you write the conductivity like this, like I described in the previous lecture, this sigma, whichever is going to multiply each and every component, is no longer identical. It's not the same sigma. So this the quantity, the conductivity along the E1 or the I cap direction is sigma 1 1, the conductivity along the j cap direction is sigma 1 2. Conductivity along the k cap direction is sigma 1 3 for your current density J1. For the current density J2, conductivity along E1 direction is sigma 2 1. Conductivity along E2 direction is sigma 2 2. Conductivity along E3 direction is E3, or your K cap direction is sigma 2 3. So as you see, this physical quantity, which was earlier considered as constant, I mean, having same magnitude in every direction, this quantity no longer has identical or same magnitude in all other direction. So this conductivity has this sigma 1 1 value along the I cap direction for J1 calculation. It has sigma 1 2 value for J cap direction along for the J1 calculation, like that. So this quantity, this conductivity is not identical in all the three-dimensional space, all the directions, I, j, cap direction. Also, this conductivity sigma is different for your J1, J2, and J3. See, for J3 is sigma 31, sigma 32, sigma 33. So once we consider such anisotropic system, we will find that this quantity conductivity is no longer a constant. It has what is called preferential direction, or the conductivity varies along that all the direction, and for J1, J2, J3 it varies. So when we encounter such kind of physical system, we can no longer define within the scope of our vector and scalar. Therefore, we have to introduce what is called just a minute, one student just text me. We have to introduce what is called this tensor algebra, which is just a mathematical tools. Okay, under tensor we are going to write all our physical system, be it a scalar, be it a vector, or some other quantity like the one we describe here, like conductivity here, which cannot be described within the scope of vector and scalar. Everything will be expressed under this tensor algebra, and that this tensor algebra tool will be can be efficiently used in describing like certain complicated anisotropic physical phenomena or engineering phenomena as well. Now, before we get into the deep details, actually we are not going to going to go into the details of this tensor analysis, because you know, your syllabus is quite vast. So I'm teaching you the vector section, and Sir Gurung is teaching you other sections, and again DPA also. So it consists of 5 units. So we cannot dwell into the deep details of this tensor analysis. It will be just a brief introduction in this undergraduate course. Hopefully, if you study in other universities and all, I think you will have, depending on the kind of course you choose as your elective, you might be studying more detail. Actually, when I was a MSc student, during our, I think that was in our third semester, we had to choose optional courses like elective courses, and unfortunately I took up a GTR course. Actually, one of my friend who is now a faculty in IIT Madras, uh, he was like, his name is Santanu Mukherjee. He was kind of quite fond of this kind of general theory relativity and all. So during our IIT days, he like we were very close, and he used to come and to my room, and we used to study together from my notes and all. He was very lazy and he hardly attends all the classes, but just before the examination he will come to my room, and he will ask me to share my notes, and we just tore up my notes into two half with staple, and then one half he will study, other half I will study, and then we will exchange later on. Then that's how uh, we used to study during our IIT days. But that Santanu Mukherjee, he is very brilliant. That time also he was very brilliant. I think he will also be very brilliant now, because being a faculty in IIT Madras, he has to be. So he was very lazy. He never did well in studies, because he missed most of the classes, especially the morning class. Morning class we used to have it around 8:30. So during winter days and all, it was very cold in Delhi. So he cannot get up for that. He used to miss 2, 3 classes in the morning. But whenever he turn up for class, like if the teacher gives what is called tutorial and raise some question in during the class, he will be the first one to come up with a very reasonable idea, and like any tutorial, he will be the first one to solve it. So brilliant but lazy. But later on he went to US for PhD. He got a degree, and then he was doing postdoctoral work in Europe and US for quite some time. I think for the past since 2019, 2019 or 2018, he is now employed as faculty in IIT Madras. So because of him, I took up this GTR course, because he wanted to study that course, and he insisted that I should also do it. So, but unfortunately, I was I was horrible at GTR course, because many things were abstract. Like you cannot realize, or you cannot have a mental. It's quite difficult to have a mental picture of uh, general theory of relativity. So I totally failed in that. I was just able to get a pass mark, nothing more. So if you go for general theory of relativity and all, I think you will get to have a chance to learn this tensor representation or tensor algebra in more details. Otherwise, if you go for some other course, some other elective optionals, I don't think you will need to study tensor anymore. But just for a general understanding, for a material scientist also, we need this tensor analysis nowadays. Especially me and Dr. Dibya, we are having this computational lab downstairs in physics department. In the physical science department, the bottom floor is for the research lab, uh, where we work on this material science. So it's a simulation. There also we encounter in this material science calculation, also we encounter a lot of tensors. So if you want to become a material scientist also, basic tensor is required. But the detailed tensor algebra is needed only for general theory relativity. So Einstein proposed many kind of nomenclature for different types of tensor. So they are quite a little bit complicated and difficult to have a mental picture. So if you ask me GTR, now also I don't think I will be able to explain after having a course in GTR in IIT Delhi. So that's what I am. Anyway, so a little bit deviated from our topic. Oh, it's 9:53. All right. So we are going to study this algebra only, the basics. Now, in order to get into that, what we need to reflect back, what we need to look at is what is called a coordinate transformation. This coordinate transformation we already discussed at the time of our curvilinear coordinate system. Now, let's say we have a point P here in space, and this point P here in space we can represent it using this coordinate system called XY coordinate system. XY. Let me define this as unprimed. Yeah. XY means unprimed. And what are the coordinate variables in this XY coordinate system? The coordinate variable along x-axis, coordinate variable along y-axis is x and y. So x and y. Now, what I need to introduce at this point itself is also that in tensor analysis, we are going to use indices. So instead of writing different alphabets like x, y, we are going to write x1, x2. So x1 means your x coordinate variable. X2 means your y coordinate variable. All right. Now the same point P in this space can also be represented using another coordinate system, which is, let's say, slightly rotated away from this original coordinate system with an angle of theta. The rotation angle is theta, but having the same origin. So using this, what is called x prime, y prime, x prime, y prime coordinate system, we can also represent the same point in space, right? So this is called, the nomenclature we're going to use is called, this is called prime coordinates. Okay. Another one was unprimed coordinates. And this here we call it prime coordinates. And these prime coordinates, the coordinate variables here will be along x prime, the coordinate variable is small x prime. Along the y prime coordinate axis, the coordinate variable is y prime. Right. So again, in tensor representation, we are not going to use different alphabet. We are going to use indices. So we are going to call this as x1 prime, and we're going to call this as x2 prime. I hope that is clear to you. So we are going to use the same alphabet x only. Instead of using x, y, and z, we are going to use it as represent it as a x1, x2, x3, like that. Now, what will be the coordinate transformation here? Can you now express your x1 here in terms of x1 prime, or let us not use this for now, indices, because I think that would make it simple. Let's say x prime. Okay, here as you see x prime, we call it as x1 prime. So can we write x prime as a function of x and y? Or can we write a transformation, or can we express x prime in terms of x and y? Right. Now, in order to do that, we have to see what is x prime here. Somebody write something in the chat box. Yeah. Please, those who join late, there is a Google form. Fill up that Google form only. Don't. I'm not going to see the chat box. So roll number 373, 133, 363, 192. Please fill out the Google form. All right. Now, this x prime coordinate variable, for representation of this point we are going to represent it using x prime, y prime, as I said. So what is x prime here? Somebody has, it's giving me trouble. Who is the CR? CR can copy and paste in the chat box once again. I don't want to see the chat message every time during my lecture. Just copy and paste the CR. Just monitor the chat box, copy and paste there. So what is your x prime here? Oops. If you look at this, this will be in this coordinate representation. This is your x prime, isn't it? Okay, this is your x prime. Now, if we are going to express in terms of x and y, x prime will be, if you look at this, Now you see that this is your x. This to this is your x. And from this point, if you, from this point, if you drop a perpendicular here along this, like this, if you drop a perpendicular here, and you say that by dropping perpendicular means this is 90 degree, all right? This is 90 degree. So what would be this? What would be this quantity? What would be this length? Can anyone tell me what will be this length here in terms of x and theta? In terms of x and theta, this will be your x cos theta. All right, this will be your x cos theta. Now you see that your x prime is extending from this to this. So what is this length? You see that this is y over here. So if you drop a perpendicular here like this is 90. Now if you consider geometry, this will be theta and this will be theta from the geometry, and this also will be theta. So if this is theta here, this line segment between this segment will be, if this is theta, this is y, hypotenuse is y, this is 90 degree, this is theta. So this means the opposite side of this right angle triangle. So this opposite side of this right angle triangle in terms of the hypotenuse, y will be y sine theta. Now you see that your x prime, which is extending from this to this, can be written as this segment between this is your x cos theta, plus this segment, which is your y sine theta. X cos theta plus y sine theta. And similarly, you can write your y prime as, so what is y prime? Oops. Y prime is between this and this is your y prime. Okay, this short segment is your y prime. Now, this is y, this is theta. So this whole length between this to this is, between this point to this point, this whole length here will be y. This is theta, means y cos theta. All right, yeah. Y cos theta. Okay, this is y. This segment will be y cos theta. Now, this is x. Okay, this is x. So between this to this segment will be x sine theta. Now, what will be this? What will be this y prime here? Y prime will be, this whole length is y cos theta, and this lower segment is x sine theta. So this y prime will be y cos theta minus x sine theta. Okay, or in fact you can write this as y prime as minus of x sine theta plus y cos theta. All right, so these are the transformation relations. Or in terms of indices also we can rewrite. So anyway, let me go to the next page. So I hope you can understand why how I write the transformation relations like this from the figure. If you don't get it immediately, please review this lecture and look at the geometry or the right angle triangle I constructed here. So here I'm constructing one right angle triangle here and another right angle triangle here. So two right angle triangles. So from this, I think you can understand that we can write this as this, or this. These are the two transformation relations. Using these transformation relations, we can express one coordinate variable in terms of another coordinate variable, where theta is the angle subtended between the two coordinate variables. So, like I said, in terms of this indices here, your xy is x1, x2, your x prime, y prime is x1 prime, x2 prime. So therefore, in terms of indices, we can write this as x1 prime, x1 cos theta plus x2 sine theta, and this we can write as y prime means x2 prime, x means x1, oops, sine theta plus x2 cos theta. So in terms of indices. Now, what is this? This quantity, let me use represent this as aij. Now let me write this. X1 prime can be written as summation of what is called, this one means 1j xj, j extending from 1 to 2. Now if you look at this x1 prime will be simply, if I express it like this, x1 prime will be simply, if you take the summation along j index, summation along j index, here one is already here, j equal to 1 means a11 x1 plus j equal to 2 means a12 x2. So you see that x1 prime is a11 x1 plus a12 x2. So here your a11 here will be what is called cos theta here. Your a2 here will be, in this coordinate transformation, it's sine theta. Similar to that, you can express this second equation x2 prime as summation a 2j xj j summation from 1 to 2. That means a21 x1 plus a22 x2. Now if you compare with this relation, x2 prime expression here, a21 will be equal to minus of sine theta, a21 is equal to minus of sine theta, a22 will be equal to cos of theta. So in general, we can combine this and this as xi here, xi aij j summation from 1 to 2, j index from 1 to 2, running from 1 to 2. Okay, I equal to 1 means x1 prime, I equal to 2 means your x2 prime. So these two set of transformation relations, you can use this indices representation, and we can simply express in terms of this expression. Okay, we can simply express in terms of this expression. So I hope up to that it is clear to you. And also, if you look at this, if you look at this here, x1 prime, if you differentiate, see, let me rewrite x1 prime here. X1 prime is x1 cos theta plus x2 sin theta, x1 cos theta plus x2 sin theta. Now if you differentiate x1 prime with del of x1 prime with del of x1, if you do that, what will you get? Differentiating x1 prime with del of the x with respect to x1 means differentiation of x1 cos theta with respect to x1 plus differentiation of x2 sin theta with respect to x1. So this differentiation, if you look at it, theta is constant with respect to this coordinate variable. So differentiation of x1 with respect to x1 is cos theta plus theta sin theta function. Theta is constant with respect to this coordinate variable x1. Differentiation of x2 upon x1. x2 is coordinate variable along the y-axis. x1 is coordinate variable along the x-axis. They are independent. So if they are independent, this is 0. So this is cos theta. So that means cos theta, what was cos theta here? You are, if you look at this, this is your a11. All right. So you can see that as written here, a11 will be del x1 prime upon del x1. And similarly, you will find that if you differentiate x1 prime with respect to x2, you will get sine theta, which is your a12, the second coefficient here. Sine theta here is this is your a12, right? This is your a12 here. Your a12 is sine theta, a11 is cos theta, and a11 is actually del x1 prime upon del x1. A12 is del x1 prime upon del x2. And similarly, you will see that if you perform differentiation of x2 prime with respect to x1, it will be minus of sine theta. This minus of sine theta is your a21. A21, you can represent it using this differentiation as del x2 upon del x1. A22, you can represent it using this. So similar like that, you will find that finally we can express this as xi prime as summation j equal to 1 to 2 del xi prime upon del xj xj. Okay, so instead of representing like here over here, aij is now replaced with del xi prime upon del xj. All right, so I think how we are replacing aij with respect with del xi prime and del xj is, hopefully it's clear to you if you just differentiate it. Okay, so finally, yeah, this is how we can represent the coordinate variables in one unprimed coordinates, or how we can relate the coordinate variables in unprimed coordinates. See, xj is simply representing the coordinate variables in unprimed coordinate system. Xi prime is representing coordinate variables in primed coordinate system. So we define two coordinate system, like I said at the beginning here, primed and unprimed coordinate system, and the coordinate variables in those two coordinate system, we can write the relation, and that relation is called the transformation equation, like this, so on. And we define what is called chronicle delta also. You know that in a particular coordinate system, like your xyz coordinate system, del y upon del x is 0, because the coordinate variables like x, y, and z are independent, right? And similarly, del z upon del x is also 0. So this is represent mathematically using what is called chronicle delta. So simply here a del xi upon del xj. So you know that del x upon del x is 1, del y upon del y is 1, and similarly del z upon del z is also 1. Now if you write x, y, z as x1, x2, x3, instead of using different alphabets for the coordinate variables, let's use the same alphabet x, but with the subscript 1, 2, 3. Then you see that xi could represent xi when I runs from 1, 2, 3. It could represent any of this xyz, and xj, if your j index runs from 1, 2, 3. So j equal to 3 means z, j equal to 2 means y, j equal to 1 means x. Similarly, I equal to 1 means x, I equal to 2 means y, I equal to 3 means z. So if you know this, like if I is equal to j, that means x, x, y, y, j, j, any of these differentiation will be 1. If I does not equal j, that means del y upon del x, del z upon del x, or del z upon del y, or del y upon del z. So when the coordinate variables, the numerator and denominator here, they are not identical, then this differentiation will be 0. So this chronicle delta function, we call it, it can be either 1 or 0. It will be 1 if the true indices I and j are having the same value, it will be 0 if the true indices I and j are not having the same value. That means I is 1, j is 2, j is 3, or I is 2, j is 1 or 3, like that. So after this, I would like to discuss, I think it's about the end of our lecture. It's 10:15 now. So I don't want to get too much into this for the first lecture. Hopefully, tonight I might be busy. Hmm, I don't know if I can take class at night this week because of one international webinar and other programs I have at night. So let's see if we can arrange class. I will let you know. Otherwise, I think that will be it for this week, and we can continue next week. Okay. Hope you have filled up your Google form. We can end the session.